Hi everyone, this is vitalmath. This will be a very unusual video and I'll explain why at the end. But today's mathematical beauty is actually about AI and a 140-year-old conjecture. Have you heard what happened recently? During the World Cup final on the 19th of July 2026, mathematician Alpöge casually posted a short message on X. He claimed that he had found a counterexample to a famous conjecture with the help of AI, Claude Fable 5 to be precise. But the biggest surprise was that mathematicians had been trying to prove this conjecture for almost 140 years, while now a mathematician working with AI appeared to prove it false in just a couple of days. That sounds surprising. But what is this conjecture about? What does the counterexample actually prove? What it tells us about the mathematics today, and what role did AI really play? As I said, this is an unusual video in an unusual format, but it's very up-to-date, at least for now in August 2026, and I hope you find it is interesting. At least I found it interesting to learn a bit more about the Jacobian conjecture. So what is the Jacobian conjecture? This is what it asks. Suppose we have a polynomial function f that maps n-dimensional complex space to itself. The Jacobian conjecture then states, if the Jacobian determinant of f is a non-zero constant, then f has an inverse. And that inverse is also a polynomial map. But what does this mean? Let's start with polynomial map. What is it? It is the transformation of points using the simplest possible ingredients, additions and multiplications of coordinates. No roots, no divisions, no trigonometric functions, only additions and multiplications. Mapping from Cn to Cn means that f takes a point with n coordinates and transforms it into another point with n coordinates using only polynomials. Next is Jacobian determinant. What is it? The Jacobian determinant is a number computed at each point that roughly measures how the map stretches, compresses or flips space around the point. When it's zero, the map locally loses at least one dimension. For example, a three-dimensional neighborhood may be flattened into a surface. When it's not zero, the map transforms the space without losing any dimension. So 3D space remains 3D, 5D space remains 5D. Think of it as a three-dimensional neighborhood that can be stretched or distorted but cannot be flattened into a sheet. There is a theorem in mathematics stating that such a polynomial map can be reversed inside a sufficiently small neighborhood. In other words, it is locally reversible. The Jacobian conjecture extends this idea from local to global. It says that if a map can be undone in every small neighborhood, it must be possible to undo it as a whole and to undo it using another polynomial. In essence, the conjecture asks whether being reversible everywhere in the small forces a map to be reversible in the large. But where did this conjecture come from? As you might have already guessed, the conjecture is named after the Jacobian determinant, which is itself named after the 19th century German mathematician Carl Gustav Jacob Jacobi. But the problem over time gained the reputation of hard problem that made many mathematicians fail. In 1884, Czech mathematician Ludwig Krauss first stated the two-variable version of the conjecture. He also presented what he believed was a proof, but the proof contained a gap. In 1939, German mathematician Otto Heinrich Keller formulated the more general version in n dimensions, so that's the conjecture how we know it today. Keller was even considered the creator of the conjecture for many years until Krauss's earlier work was rediscovered. At least 5 published proofs were later found to contain errors. All of them attempt to prove that the Jacobian conjecture was true. For example, a 2005 paper literally titled "A Proof of the Plain Jacobian Conjecture," attempt to prove the two-dimensional case, but it was withdrawn after an error was discovered. So no counterexample to the complex Jacobian conjecture had been found. Many mathematicians regarded the statement as intuitively plausible. Even Yitang Zhang, the mathematician who later made a major breakthrough toward the twin prime conjecture, was derailed by the Jacobian conjecture. In 1991, he wrote his PhD thesis at Purdue University on the problem, but his work relied on a lemma from his advisor that was later found to be problematic, and it didn't produce a valid solution. Zhang then spent years outside mainstream academic research before becoming famous for his breakthrough on bounded gaps between prime numbers in 2013. But why did attempts at the Jacobian conjecture keep failing? The central difficulty was controlling the map's behavior at infinity, far beyond any finite region that we can inspect directly. In plain English, Krauss understood how the map behaved around ordinary finite points, but his argument didn't successfully rule out the possibility that the map could fall back onto itself when its coordinates became arbitrarily large. That was the gap in Krauss's argument in 1884, and controlling this behavior at infinity remained one of the principal obstacles for almost 140 years. So what did Alpöge find? Alpöge posted an explicit counterexample, an explicit polynomial map from three-dimensional complex space to itself. The map consists of 3 polynomials. Its Jacobian determinant is exactly -2 at every point. That means that the map is locally reversible everywhere. However, the three different points are all sent to the same output. Three different inputs produce exactly the same output. Therefore, the map cannot be reversed. This disproves Jacobian conjecture in 3 dimensions, but actually it's easy to generalize it to or larger dimension. You can add the extra coordinates that remain unchanged, and the same construction produces counterexamples in every dimension above 3. But what's interesting, the 2-dimensional Jacobian conjecture remains open. So AI didn't solve the entire Jacobian problem. It disproved the general conjecture in dimensions 3 and above, but the historically central 2-dimensional case remains open. So what does the fact that this conjecture is false tell us? First of all, it actually creates extra work for mathematicians. Because, look, if the conditions from the conjecture are not working, mathematicians now need to find out which additional conditions would make a similar statement true. Plus, they now need to understand why the 2-dimensional case behaved differently. And in addition, the counterexample also affects several related problems in algebra and geometry. One immediate logical consequence is that the Matthew conjecture for the group SU3 must also be false. There are some other chains of implications that show, for example, that Zhao's vanishing conjecture and the image conjecture are false in at least some finite dimensions. And the discovery has already generated further results. Researchers have produced explicit counterexamples showing that the Gaussian moments conjecture is false in every dimension from 3 and upwards. Alpöge's map has also been transformed into a counterexample into the Hessian conjecture, showing that it is false in dimensions 5 and above, while in 4-dimensional Hessian case remains open. However, not all these results follow simply by substituting Alpöge's 3 polynomials into another problem. Some are direct logical consequences, while others are new discoveries inspired by the original counterexample. But what is interesting about the example itself? The interesting point is how strange the counterexample is. Terence Tao noticed how unusual the counterexample is by comparing the number of available coefficients with the number of cancellations required to get constant as a result. The map is defined by 3 7-degree polynomials. In the general case, 3 polynomials of degree up to 7 contain about 360 adjustable numbers, the coefficients multiplying terms such as xyz, z to the power of 7, x squared y. When we use those 3 polynomials to calculate the Jacobian determinant, we obtain a new polynomial, and each coefficient in this new polynomial is determined by combinations of these original 360 numbers. So, for the determinant to equal exactly -2, every non-constant term in it must disappear. That creates up to 1329 cancellation conditions that the original 300 coefficients must satisfy simultaneously. So it sounds like a miracle, and in order for it to work, the map must contain something like a hidden structure that forces many cancellations at once. That's the hidden math beauty. This makes this example look almost miraculous. It doesn't resemble something that could easily be discovered through blind brute force analysis. Terence has already spent several days trying to digest the counterexample to understand the hidden structure that makes all these cancellations possible. And his analysis suggests that the counterexample is connected to a deeper geometric structure involving polynomial factorization. So this ugly-looking formula with 3 polynomials is not simply a random collection of terms. It is the compressed result of a more organized structure, which we're yet to discover. However, we still don't know exactly how Claude originally found the example. The full prompt, complete conversation, the amount of human guidance, and the unsuccessful attempts have not been published yet. So what does it tell us? Are LLMs becoming mathematical problem solvers? This result shows that LLMs can help make real mathematical discoveries, but they are not yet independent mathematicians. Alpöge chose the problem, guided the search, and recognized that the answer was important. He was the one to make the post. AI can explore many possibilities and suggest some unexpected solutions, but humans still provide the question, judgment, explanation, at least for now. But where is the beauty in this story? I think there are 3 different kinds of beauty here. The first is the beauty of the conjecture itself. The tension between the local and the global. Even without AI, just think about it. At every individual point, the map behaves perfectly. It never flattens space, never loses a dimension, and can always be reversed inside a sufficiently small neighborhood. And yet, when we look at the whole space, distant points can still collide. The conjecture asked whether perfect local behavior everywhere was enough to guarantee perfect global behavior. And counterexample shows that it is not. The second kind of beauty lies in how the conjecture was disproved. A mathematician working with AI produced an unexpected example. The entire result fitted into a short social media post on X. Other mathematicians immediately checked it, formalized it, tried to understand its structure, and began deriving new results from it. This may be a glimpse of a new way in which mathematics is done today. Humans formulate questions and recognize important ideas, AI systems search for unexpected objects, and the wider mathematical community immediately verifies, explains, and brings results to other industries or other parts of mathematics. The third kind of beauty is also a reminder that we can be wrong. For almost 140 years, most attempts focused on proving that the conjecture was true, because the statement looked so natural and convincing. But mathematics doesn't care how plausible an idea is. It doesn't care how long the conjecture has survived or how many brilliant people have believed in it. Everything has been overturned by 3 explicit polynomials and 3 points that everyone can check and validate themselves. So we should be mindful about this. Let me know in the comments what other conjectures you think might follow the same path, what ideas in mathematics everyone is believing to be true, but who knows which counterexamples we can find. That's all for today. So why is this a strange video? Well, there are no proper animations, no proper editing. This is probably the worst video I've ever made, but this channel is about the beauty of mathematics. I hope this story and its messages are still interesting, because math beauty should be above all of those technical challenges. Nevertheless, in 2 weeks, don't miss a new video in a better quality. Hope you enjoy it, and as always, think and enjoy the beauty of mathematics. See you next time.